Welcome to the deep dive. Today we're getting into something huge, something invisible, but something that, well, runs the whole show. Gravity.
That's right.
And I think most of us, we get the basics. Apple falls, Newton, maybe something about orbits. But that picture, it's not the whole story, is it?
Not even close. Gravity is fundamental. It dictates how planets move, how galaxies form, why we're stuck to this planet.
So our mission today for this deep dive is really to dig into what gravity actually is. We want to go past that high school physics level.
Yeah, we'll look at Newton's idea of the tug, but then really jump into Einstein's, his whole revolution, geometry, spacetime.
And tackle some maybe counterintuitive stuff, like why don't we feel the sun's gravity more, given how massive it is?
Exactly. And the big one, what keeps this whole solar system from just, flying apart or crashing together? It's this incredible balancing act.
Right. A very precise dance.
So maybe the first thing, before we get into the weeds of space-time curvature, what's the biggest sort of misconception we need to clear up right at the start?
Good question. For me, it's probably still that lingering idea of gravity as just a force, like magnetism, but for everything. That Newtonian pull. Why was that not quite right?
Well, it worked mathematically incredibly well for a long time. Newton's laws, they let us predict orbits, tides. But how does that pull act instantly across vast distances? That was the mystery.
It didn't explain the mechanism.
Exactly. The biggest leap we need to make is understanding that gravity, according to Einstein's general relativity, isn't really a force between objects in the way we normally think. It's something else entirely.
Okay, let's unpack that then. General relativity. This is where it gets really mind-bending, but also beautiful. What did Einstein propose gravity is?
So Einstein basically reimagined the universe. He said gravity isn't a force acting through space, it's a feature of space, or rather space-time, this four-dimensional fabric.
Right, the cosmic sheet or trampoline analogy people often use.
Yeah, it works pretty well. Imagine laying a heavy ball like the sun onto that trampoline. It creates a dip, a curve, a distortion in the fabric around it. Now, if you roll a smaller ball, say the Earth nearby, it tries to go in a straight line, but the fabric itself is curved. So following that straight line through curved space looks like an orbit to us.
So the object isn't being actively pulled towards the sun by some invisible rope?
No, it's just following the contours, the geometry of the space-time that's been warped by the sun's mass. It's moving straight, but in a curved space. That is gravity.
That's a huge shift in thinking. Objects follow the straightest path available in a landscape warped by mass.
Precisely. And everything with mass does this. The Earth warps space-time around it. You warp space-time around you just infinitesimally. This microphone does.
Okay, but then that raises the obvious question. If my coffee cup has gravity, why isn't my pen slowly sliding towards it across the desk? Why don't we feel the pull of, say, a big truck driving past?
Yeah, that comes down to two key things, mass and distance. They're intrinsically linked in how gravity works.
The mass-distance rule. We know Earth is enormous, but the sun is way bigger. Yet we feel Earth, so distance must play a huge role.
A huge role. The strength of gravity drops off really fast with distance. It follows what's called an inverse square law. Double the distance, and the gravity is only 1/4 as strong. Triple it, it's 1/9.
Okay, wow, so things nearby have a massive advantage.
Exactly. The Earth's center of mass is, about 6,400 kilometers right beneath our feet. And its mass is colossal compared to anything else nearby. That combination of huge mass and relative closeness just completely overwhelms the tiny gravitational influence of your coffee cup or even mountain range nearby.
So we're just bathed in Earth's gravity and everything else is basically noise level.
Locally, yes. Earth wins the gravity contest here, hands down.
Right. But then let's scale up the sun. It's about 330,000 times more massive than Earth. That's staggering. If mass curves space-time, the sun's curve must be immense. So why don't we feel that? Why aren't we constantly aware of being pulled slightly towards the sun?
That's a really good point, because the sun's gravity is acting on us, on every atom in your body right now.
But we don't feel it like we feel Earth's gravity pulling us down.
No. And again, it comes back to distance being the great equalizer, or maybe the great diminisher here.
The trump card again. Even against that massive mass difference.
Absolutely. Remember, we're about 6,400 kilometers from Earth's center, but we're about 150 million kilometers from the sun.
Okay, that's a big difference.
It's enormous. And because gravity weakens with the square of the distance, that factor just crushes the sun's influence at Earth's surface. If you actually calculate it, the pull of the Earth beneath your feet is something like tens of thousands of times stronger than the direct pull of the sun on you.
Tens of thousands. Okay, that really puts it in perspective. So they have different jobs almost.
That's a great way to put it.
Yeah.
The sun's gravity dominates the large scale it dictates Earth's orbit, keeps the whole planet tethered over cosmic distances. But Earth's gravity dominates the small scale. It keeps us tethered to the surface, holds our atmosphere, gives us weight, local versus solar system level.
Okay, let's talk about that solar system level then. The orbit. If the sun is constantly warping space-time, creating this well, and Earth is constantly rolling around in it, why doesn't it just spiral in? What keeps it stable?
Yes. The stability of orbits. This is where it gets really elegant. It's about achieving what we call kinetic equilibrium. It's a balance.
A balance between
Two things. One is gravity, that constant inward curve, the falling into the sun's space-time well that we talked about.
Okay, the pull.
And the second thing is the Earth's own motion. Specifically, it's sideways motion, it's inertia. Earth isn't just sitting there. It's moving incredibly fast sideways relative to the sun. It's lateral velocity.
And how fast are we talking?
About 107,000 kilometers per hour, or roughly 30 kilometers per second. It's blistering speed.
Wow. Okay, so gravity pulls in, but the speed keeps it moving sideways.
Precisely. Think of it like this. This is the classic way to visualize it. The Earth is constantly falling towards the sun due to gravity, but its immense sideways speed means that as it falls, it also travels a huge distance horizontally.
So it keeps missing.
It keeps missing. By the time it's fallen, say, a meter down towards the sun, it's traveled so far sideways that the sun is still the same distance away, effectively. It falls, but it moves sideways enough to constantly overshoot. It's in a perpetual state of falling around the sun, never hitting it.
That's quite a concept, perpetual falling, never landing. So that stability, that missing, depends entirely on having the right speed for its distance.
Absolutely critical. The whole solar system's architecture relies on this. Gravity gets weaker the further you are from the sun.
Right. The inverse square law again.
So planets further out don't need as much sideways speed to stay in balance. Planets closer in, where gravity is much stronger, need to be moving much, much faster to avoid falling in.
Can you give some examples, like Mercury versus Neptune?
Sure. Mercury is right up close to the sun. The gravitational pull there is intense. To counteract that, Mercury has to zip around at about 47 kilometers per second. It's incredibly fast.
47 kilometers a second. Okay.
If it slowed down significantly, gravity would win, and it would spiral inwards.
Yeah.
Now contrast that with Neptune, way out in the distant solar system.
Where the sun's gravity is much weaker.
Much weaker. So Neptune doesn't need nearly as much speed to stay in its stable orbit. It ambles along at a comparatively leisurely 5.4 kilometers per second. Still fast by our standards, but way slower than Mercury.
So each planet is fine-tuned. Its speed matches its gravitational environment perfectly.
Exactly. The solar system is stable because each planet possesses the necessary orbital velocity to balance the sun's gravity at its specific location. It's this precise calibration of speed and distance against gravitational pull.
It's less like a sturdy machine and more like a perfectly balanced mobile.
That's a good analogy. It works because everything's in the right place, moving at the right speed.
Yes.
It's all interconnected through space-time geometry and inertia.
Okay, so we've got Earth's gravity, the sun's roll, the orbital mechanics. Let's zoom out one more time. What about really, really big things like other galaxies? Does Andromeda's gravity affect us here?
Technically, yes. Every mass exerts gravity on every other mass, no matter how far. So the collective mass of the Andromeda Galaxy, millions of light years away, does exert a gravitational influence on Earth, on you, on everything here.
But presumably, given the distances involved.
It's incredibly tiny. That inverse square law, again, working over millions of light years, reduces the effect to something utterly negligible on a local scale. Even the gravity of our own Milky Way galaxy, while much closer, doesn't really mess with, say, Earth's orbit around the sun.
So where does the galaxy's gravity come into play then?
It acts on the solar system as a whole. Just like the sun dictates Earth's orbit, the combined mass of the Milky Way, especially concentrated towards the center, dictates the orbit of our entire solar system around the galactic center.
So we're orbiting the sun, and that entire orbiting system is itself orbiting the center of the Milky Way.
Exactly. It's orbits within orbits, all governed by the same principles of mass curving space-time and objects following those curves based on their velocity.
Wow, okay. So let's try and wrap this up. We started with the simple apple falling.
And we moved through Newton's idea of a force, which was useful but incomplete.
To Einstein's much more profound picture, gravity as the actual shape, the geometry of space-time being curved by mass.
Right. And we saw how distance is key, why we feel Earth's gravity overwhelmingly. Even though the sun is vastly more massive, Earth is just so much closer.
And finally, the reason we don't crash into the sun or fly away is this delicate, balanced kinetic equilibrium. Earth's incredible sideways speed constantly makes it miss the sun as it falls along spacetime's curve.
A speed precisely calibrated for its distance, just like every other planet.
It really highlights the sheer precision of it all.
It does. And maybe that leads to a final thought for you, the listener, to take away. Think about this. Every object with mass warps space-time. The sun, Jupiter, even asteroids flying by. And Earth is speeding along at 107,000 kilometers per hour.
Constantly adjusting.
Constantly. Moment by moment. Its trajectory has to adapt almost instantly to the subtle, ever-changing curves in space-time created by the positions and masses of everything else in the system. It's not just following one simple curve, it's navigating a dynamic gravitational landscape.
What does that constant, high-speed, precise adjustment tell us about the underlying coherence or calibration of the universe itself? That this stability holds second by second across such scales.
It makes you think, doesn't it? The universe isn't just static, it's this incredibly dynamic system in perfect high-speed balance.
A lot to ponder there. Well, thank you for joining us on this deep dive into gravity.
Yeah, it's been fascinating.
We really encourage you to keep digging into the source material on this. There's always more to learn. We'll see you next time on The Deep Dive.